So in the analysis part of the separations lab, we're focusing on a couple of these goals that I had. So some of these goals we already did in the experimental portion, but in this second part, it's can you be able to measure and calculate an RF? So we'll just practice going over that a little bit. I know you got a little confused with how to process it and which dots to use. We'll go through an example. The other thing is the selective precipitation. How do you design a scheme, and how do you figure out stoichiometrically how much of the reagent you need to fully precipitate out the ion, which depends on the scheme. So let's go through a couple examples. All right, so again, on the analysis of the column, there's really not much to do except to record your observations. We really did that in the lab. But for the TLC, we need to calculate these RFs. So for each color in each lane, you need to measure the distance from the starting point to that colored blob, the farthest edge of that colored blob, and then measure the distance from the starting point to the solvent front. That only needs to be done once, but and then divide the colored blob's measurement by the solvent front measurement to get the RF. And I know that when we were doing this, sometimes especially with the water, you took the TLC out and you drew the line and then you set it aside and the water kept going up. And so as the water kept going up, so did the dots, especially because one of our components had a very high RF. It's almost the same distance as the solvent front. So when I divide a number by itself, I'm going to get a value of 1. So we're going to see close to RF values of 1s for the red component. But in your case, I just want you to do your best. Let's go through the process. Again, I explained that this is not an optimized TLC and there's issues with it. And you'll talk more about how to optimize a TLC and design it in organic, but we get the idea of how to run a TLC. All right, so I am using this 2-spot. So in other words, the vocabulary we use a spot for each of the ones we started with here. So here I had 1 here and 1 here. We had 3 spots on our TLC. That's okay. And then for each spot, I can have multiple components. Each colored blob in the lane that is going up is a component. So I can quickly look at this spot here and say there are 3 components. Possibly 4 if there was some left, but that's you can't really say. So you'd say 1, 2, 3 spots. So 3 components, or 3, let's say, yeah, I don't want to say spot because we're calling this the spot. And so these are the components. And so not knowing ahead of time what you're going to have, the table is large. It's for each spot, assume that you could have up to 3 components. But in our 1 spot, 3 components. But in our specific TLC, the left spot had 3 components and the right spot had only 1 component. In our TLC and lab, we had 1 component, and 2 components. So we had 3 spots, and so there's a lot where it's NA. All right, so we're going to measure the distance for each one. So again, I've written down spot 1 could have had up to 3 components, and it did. Spot 2 could have had up to 3 components. It only had 1 component. So these other 2 components, I wrote NA. And then I've identified yellow, blue, purple, just so it makes it a little easier than the original description. We didn't know what we were going to see, so it's just spot 1, component 1. But now that we can see it, you can go ahead and label and makes it much easier. So I'm saying left and right. You on yours might be, spot 1, 2, 3, or however, left, right, and middle. I don't know. Okay, so I measured the distance, and so I'm using this. You should have already done this in lab, but if you find that there's an issue, note that because you kept your TLCs in your lab notebooks, each partner has 1 of them. If you realize there's an issue, you just got to get a nice ruler and redo things. So I'm measuring from this line. Because I'm measuring from this line, I just lined up this 0 right on that line, and I'm going from this particular ruler scale has a negative area where if you're not starting exactly at 0, that's weird, but it's fine. And then I wrote these out to the nearest half of a tenth of a centimeter, 100th of a centimeter, whatever, to the nearest 5 or 0. And you can check me. It's a little hard when the rule is not right next to the spot. I know that, but I measured it for you, but you can just make sure. So I have 2.85. If I look at this farthest edge, You can see it's like right here, etc. Note that on this particular example that I used, this blue spot isn't quite the same as this blue spot. So it's 3.20, where the one on the left is 3.25. The one on the right is a little bit shorter, so it's 3.20. But also notice my solvent line's a little wonky, and that happens. It's legit. So if I measure the solvent line here, it's at 4.50. But if I measure it here, it's at 4.45. And that will affect my, the ratios. Now again, we don't care how far the solvent front goes. We want to know the ratio. In other words, proportionally, how far does the component go compared to the solvent? So when we divide it off, so these first three, I'm using 4.50 and dividing by it because that's the solvent front for that spot. The other one's 4.45. Now you may have your solvent front is the same for all spots, and then you just have one value. But then and because I went to full precision, so I went to the second decimal place, even though it's hard, because I did that, this is now 3 sig figs, so I can keep 3 sig figs in my RF. Note, we would expect that the blue component, it's the same component. Well, I mean, in our lab particularly it is. This doesn't have to be, but usually you're doing a TLC of the mixture, original mixture, and some of the things. So often you're going to see, or you have identified pure substances and you're trying, so I'm going to say, I'm trying to see if component X is in my mixture. And I take a pure sample of whatever X is, and I'll run it in one lane, in one spot, and in another lane, I'll run the mixture. If I get the same R value, that's supporting evidence that, yeah, that component is in this mixture. So there's a variety of ways you can use TLC. Anyways, I get my R values. Note that the blues are pretty similar. This is 719, 722, and within the level our precision. Obviously, we went very short distances. The longer distance you go, the more precision you get. This is probably pushing it to really say. We can calculate 3 sig figs. It's probably more like 2 sig figs, in which case they would be both 0.72, and they're the same. All right, so that's the TLC. Now let's move on to selective precipitation. Again, the scheme is we have 3 ions, and we're going to precipitate it out. So if we had a variety of ions I'm going to do an example with 2 ions, but you're assigned an example with 3 ions. And this is kind of showing the 3 ions. So I have 3 ions, yellow, red, blue in here. I'm going to add a reactant that would just precipitate the blue ion. Again, we'll talk about how do I find that out. And so if it only precipitates the blue, but it doesn't precipitate the yellow and the red, then the blue becomes precipitate, which means when I filter it, the blue will be sitting on the filter paper and the yellow and red will be left in the beaker underneath. I use test tubes because they're easier to draw, but usually you have a beaker underneath or a flask underneath the filter, and all the aqueous ions that didn't precipitate would be left in here. And realistically, I'm drawing the fact that it's not a perfect process. There might be still a little bit of the blue ions in there, but very little, almost none. And then now that I have only yellow and red, maybe I have a reagent that would precipitate blue and red, but since the blue's gone, it now only precipitates the red because that's all that's left. So then I would add that reactant and the red precipitates and the yellow remains aqueous. And then if I filter that, I'll have red on solid. The red solid will be on the filter paper and the yellow will be left in the flask. So at the end, I have 3 containers: a filter paper with the blue solid, a filter paper with the red solid, and a flask left over from the filtration that has the yellow ions in it. It's not solid, they're aqueous. So that's the concept of, now I have separated this mixture, and the yellow and the red and the blue are in 3 separate containers. So let's talk about how we go through doing that. Again, just reminding you about precipitation reactions. It's not the only way to make precipitate, but the most common way is it's happening by a double replacement strategy. I take an ion, 2 ionic components, because of course, realistically, when I write this M plus or this Ma, in our reagent, we're just writing the ions. This is not a good example. So my point was that if I write copper 2 plus, I can't just get a bottle with copper 2 plus. There has to be another negative ion in that solution countering it out. So I can have the ions separated in solution. They could be, aqueous and dissociated, but there has to, the overall solution has to be charge neutral. So copper 2 plus might come as copper chloride, or as copper sulfate, or as copper nitrate. I don't know. So there'll be some other ions in there, but those, as we remember from our net ionic equations, they're spectator ions. So I'm not showing them in the reaction schemes that I'm going to do, but they're there. You could, they're fine. But so the general net ionic equation is I find a cation in solution, and I have, or an anion in solution, and I add a reagent that has Y minus, that these two precipitate, and I make a precipitate. Again, this is generic. I'm not showing any subscripts because these are +1 and -1, so it goes off easy, but you have to be careful about charge balance. So you're swapping. If I'm not looking at the net ionic equation, but I'm rather looking at the molecular, I have some reagent. It's aqueous. It's a source of these M cations. I have a mixture that has Ma, and that has M cations in aqueous form. And I have a reagent By. And I've chosen that reagent because Y will precipitate with M. So this is my source of Y minus ions. And then I end up getting my precipitate, and then I get, other ions. Again, this is aqueous, so these would be, the B ion would be left behind, and so would the A ion. That's fine. And again, be careful. These are not, these is just showing a +1, -1 charge. There can be subscripts involved if their ions are not the same charge, and that frequently happens. So again, we're determining, if I want to just predict the products of a double displacement reaction, first I have to determine what are the cation and the anion of each reactant. In our case, we're just going to give you the cation that's in the mixture already. And then I'd have the cation and the anion of the reagent that I'm going to try and use. And then I'm going to do a swapping, considering charge balance, make sure, and figure out the products that I'd have. I'd have a compound and then the other ion left over. And then go to the solubility table and determine if any of the compounds that I'm making are insoluble. If they're insoluble, they're solids. I've made a precipitate. So that's how you'll have to go about doing this. Let's go through a specific example. And this is just showing you a couple of examples of double displacement reactions. But again, so let's talk about how do you design a scheme. So I've got some ions, I've got some reagents. So the first step is that you're going to predict the products for every possible combination, every ion in the mixture with each reagent. So I'll start with reagent 1. What does ion 1 do? What does ion 2 do? What does ion 3 do? So I get 3 possible products. Then I do the same thing for the second reagent, and same thing for the third reagent, until I have used up all my reagents and all my ions. So I've considered all. So we have 3 reagents, 3 ions. So we're going to have 9 possible reactions. Write them all down, grouped by the reagent. And then you're going to use your solubility table and determine which ones are solid. Then you're going to look at each reagent, and I'm looking at the set of 2 if we have 2 ions, or 3 if we have 3 ions. I'm looking at the set of reactions, and I'm seeing, do I have just one precipitate? If I have just one precipitate, then okay, I have a scheme, because only one ion would precipitate out, and then I could separate that ion out. That's what we're looking for. After I've done that, I would then go, if I had more than 2 ions and I needed to do another reagent, then I would look at the other reagents and do the same thing. However, now I'm considering that the first ion is gone, so I ignore that one, and I'm only looking at the remaining ions. If there would be 2 ions left, because I started with 3 and I precipitated the first out, then I'd have 2 ions left, and I'm looking, does only one of them make a precipitate? And then I go through until I have all my ions separated and I have a scheme. So then I'd have an order, like which reagent would I use first? What would precipitate out? What would remain solid? And the precipitate, of course, is going to be on the filter paper when I'm done. And anything that didn't precipitate, the other ions, would be in the solution. And then come up with your product. All right, so you're going to do that till all ions are separated. So let's go through an example. I'm only using 2 ions, potassium and copper 2 plus, but you have 3 ions in your example. And I have 3 possible reagents: sodium carbonate, sodium hydroxide, and sodium sulfate. So now I predicted the products, right? I have 2 by 3 is 6 total reactions. So I've predicted all the products. I do eventually need them balanced. So remember, when you come up with these products, these reactions may not be balanced. That's okay. You just balance them. All right, so here's my set. And now I'm going to go to the next page. Remember, the solubility table from the manual is here, but it's also in the manual. And I'm going to use that, and I'm going through all of these products: K2CO3, CuCO3, KOH, CuCOH2, K2SO4, and CuSO4. I'm looking for all of them. These are the only two that are solid. So now I'm going to look reagent by reagent. First off, I see sodium sulfate. There are no precipitates. It's useless. Sodium sulfate is not going to be useful with these ions at all. Then I look at the other two. Okay, in sodium carbonate, I have two ions, only one precipitates. That would effectively precipitate out copper. Same thing with NaOH. In this particular case, either one would work. So you pick one and you move forward. I could have designed it with either one. But now I have a scheme. If I use sodium carbonate, it will precipitate out the copper 2 ions, leave the potassium ions alone, and then I can filter it, and the copper ions will be in the form of copper carbonate on the filter paper, and the potassium ions will be aqueous and in the solution. All right, now that you've figured out your scheme, you have to do the numbers, the quantitative selective precipitation. So now I'm going back and I'm adding in numbers. Suppose, I picked the sodium carbonate, but we could have done this with the sodium hydroxide as well. So suppose the sodium carbonate came in 1 molar. So we have 1 molar sodium carbonate. And we're going to assume that the original K plus was in the form of 1 gram of KCl that was dissolved, and the original copper 2 plus was in the form of 1 gram of copper chloride. Remember, when I take these soluble compounds and I put them in water, they're going to dissolve and dissociate, and I'll have the ions. I'll also have some chloride ions in there, but they're spectator and we're not using them. So how many milliliters of the reagent, in this case sodium carbonate, must be added to fully precipitate out an ion? We are going to go back to our scheme, and we're focusing on the one reaction that's making the precipitate. In this case, the copper with the sodium carbonate is making copper carbonate, which is the solid, and some extra sodium ions. And then we're going to use our 5-step stoichiometry process. Balance the reaction, find what I know and what I don't know. What's my given, what's my needed. Get the thing I do know into moles. Use my coefficient ratio to get from the moles that I do know to the moles that I don't know, from the given to the needed. And then I go back and look at what units do I need. So in this case, I need milliliters of sodium carbonate, 1 molar sodium carbonate. So I'll try and get from moles of sodium carbonate to milliliters of sodium carbonate. So let's go through it specifically. So in this case, I already had the balanced reaction. We had done that. So notice that it's 1, 1, 1, 2. So I find the amount. So next step is find the given. This is the one I'm given. I'm given 1 gram of copper chloride. That's enough to determine the number of moles. I am given 1 molar of sodium carbonate, but it's asking me how many milliliters of the reagent do I need. So it's the thing I need to find out. Plus, as you know, for moles, I need 2 things. I need the molarity and the milliliters to determine moles. So it's not, I don't have enough to figure out how many moles of sodium carbonate I need. That's the thing I'm trying to find. And then I'm going to find the moles of the given. Since the given is the copper in the copper chloride, I'm going to start with my 1 gram of copper chloride, divide by its molar mass. But now I have to recognize, because the subscript of copper and copper chloride is 1, that each mole of copper chloride will get me 1 mole of copper 2 ion. If there was a subscript of 2 or 3, I now have to consider that subscript. So if it was potassium 2 chloride, oh no, that wouldn't be right. So potassium 2 carbonate, and I was making potassium carbonate, then each mole of K2CO3 would make 2 moles of K plus ion. So be careful about that. In this case, it's a subscript of 1 for the copper, so this is 1 to 1. So I end up with 0.007437 moles. Now I consider, okay, if I have that many moles of copper, how many moles of sodium carbonate will I need to fully react it? So I'm using the coefficients. In this particular case, it's a 1 coefficient for the sodium carbonate and a 1 for the copper. So it's a 1 to 1. It's not going to change the number of moles. It's the same number of moles of sodium carbonate that I need. And now, but that didn't want to know how many moles. They want to know how many milliliters. So I'm using the moles that I just found with the molarity to determine the milliliters. So in this case, I can use the molarity as a conversion factor. So I have my 7.00743 moles of sodium sulfate. 1 molar means it's 1 mole per liter, which means I can flip it and put 1 mole per liter. So that's my molarity. And then I have to convert to milliliters, so I've added on the conversion there. So it would take 7.44 after rounding of 1 molar sodium sulfate. So I've now got the amount. And you would have to do that twice, right? Yours is going to be a little bit trickier. You have 3 ions, so you need to pick 2 reagents. So you're going to do the whole thing, but you want to do it stepwise. First, look at it, which reagent would work to figure out that you can use that would just precipitate 1 ion. So do that one first, determine what it's going to filter out, and then look at the other reagents. Cross out the one you've already filtered out from the first reaction and look at, is there just 1 ion that's made? If so, you can use that one second. So you're going to figure out 2 reagents that would separate them into 3 piles, like that original scheme I showed. So, and then you have to do 2 stoichiometry problems, one for the first reaction with the first reagent and one for the second reagent. But the steps are the same. Good luck.